forgot about that. So should be streaming in a few seconds now. There we go. And I'm also going to pin the PDF that Omer is posting. So I'll pin that one so people can find it more easily instead of having to dig through all the messages, because I'm expecting today to have quite a bit of traffic in the text channel. There we go. So we're going to get started. So we'll start with the instructions. Not really that much different from exam 1. Discord channels will be disabled for that day, and direct message me if you need clarifications. The document is individual, so this one is only for the person with the ID of 00068887, and that's me. And keeps going. No collaboration, but other than that, online and offline resources can be used. So that means using Logisim with the processor simulator is perfectly okay. In fact, you might want to use that as a way to help you to answer some of the questions. The other kind of resources that you might want to refer to at least would be the assembler. The assembler can come in handy, on maybe a few questions. Let's see, what else is going to be helpful. All of the class notes, all of the modules, can also be helpful. On that day, do not share or discuss the exam with anyone. So basically, just on that day. After that, everything is going to be okay again. Again, grading is based on explanation and steps and demonstration of understanding of the knowledge and problem-solving skills, and not so much the final answer. So today I had kind of an interesting conversation with someone from a different class. So it's not one of the students in this particular class. And that student mentioned that a lot of steps have been shown, and the implication, I'm guessing, was well, there has to be some points. And then I had to say, well, but the steps have to be correct. I'm not weighing things by bulk. Okay, I'm not looking at okay, you get X many points for this many lines of text. It has to be correct in order to get points. Write the answer in this document interleaved within the questions, and do all your editing in document. Now this is really kind of important because I don't want to see any massive copy and paste from an outside source. Let me see. No. This is not a test. This is the practice test. We talked about this on Tuesday or last Thursday, I think, that we'll have a practice test today, and then the Thursday after spring break is the actual exam. So that is that. You can indeed copy and paste. Okay, so I'm not saying copy and paste is not allowed. It is allowed as long as it is from the same document. And also, if those are images that you have created, like some people prefer to handwrite stuff, so they would kind of write the answer on sheets of paper and then take pictures of those sheets of paper and then turn those in. That's perfectly okay. But for people who want to do it that way, they have to allow for the time needed in order to upload and attach the images into the Google document. So I'm not going to let people have extra time because they're using a sheet of or sheets of paper to write down the answers. All right, with all of that said, here's question number 1. So question number 1 is a circuitry, and I did not specifically identify which one it is, even though the labeling of the pins are pretty clear about which this particular circuit is. But the idea is to ask the question about what happens when the input pins are in a particular state. So in the first part of the question, I'm asking, assuming En is a 0 and assuming D is a 0, what can we know about the states of the various components within this circuit? So let's identify the components. The input pins you don't really have to say anything about because this part here is already telling you what the states are as far as the input pins are concerned. So now what we need to do is to do a propagation analysis, which is really just a fancy name of following the changes. Okay, so what we do is we look at where D is going into. So since D is going to N1 and N1 is a NAND gate, so we can determine the output of N1 right away, right? So in the answer, we can type something like N1.out becomes 1 because D is 0 and N1 is an NAND gate. Okay. In other words, you don't have to give me the entire truth table of NAND, just mentioning because it is a NAND gate and one of the inputs is a 0, that guarantees the output to be a 1 already. So that's basically just the explanation that I need. So N1's output is now determined, and now we want to look at potentially N2. Can we determine the output of N2? The answer is yes, we can do that too. So N2.out becomes 1 because En is 0 and N2 is an NAND gate. There we go. But at this point, we now look at N1 and N2, the outputs of N1 and N2, and we see how they get to the SR latch SR. But we cannot do anything about that. Okay, so SR is just maintaining its state. So SR maintains its quote unquote current state because both S and R are ones. So that means I can't really say what the Q and the NQ pins would be because I was not told the initial state of the SR latch, so I can't really deduce what Q or NQ should be, and my analysis basically has to stop here. So are we good so far with the answer of this part? Okay, looks okay. All right. So now we move on. So assuming this is the previous state, now we make a change. Okay, we change only one of the pins, where D becomes 1. So now you have to look at the picture again and say if D becomes 1, what's going to happen? So now it gets a little bit tricky because En also goes to N1, and as a result, the output of N1 does not change. So that's what we're going to say here. Okay, so N1.out remains as 1 because En is 0 and N1 is a NAND gate. There we go. So now we look at N2, see if N2 is going to change its output. So here's N2. En remains as 0, so the explanation from before is still valid. N2 continues to output 1 because En is still a 0. So that's what we're going to write here. So we'll say N2.out remains as 1 because En is 0 and N2 is a NAND gate. There we go. No, I am not going to have a lab tonight, simply because we are not going to have time to go over new material for a new lab. But for those of you who want to kind of get a better understanding or get more practice, with the processor, I can suggest a few things that you guys can do. But we'll go over the practice test first, and then we'll get back to that portion. All right, so now we basically say, okay, so this is the nice thing about using Google Doc is you can just copy and paste. And in case your computer crashes or your internet, has a problem, that lasts only a few minutes, it's okay because as soon as you do any type of editing, it is quote unquote saved already. So there's no need to worry about, oh, I forgot to save the file and then my application or my entire operating system just crashed. It's not a big deal. Okay, just switch to a different device, different computer, sign in, and you can continue. Alright, so now we look at the next state where En and D are both changed at the same time. So now we have to go back and take a look at the circuitry here. D becomes 0 and then En becomes 1. Nope, the other way. Nope, that's right. Okay, En becomes 1 and then D becomes 0. Alright, so now we have to perform the analysis, and basically we need to know what this circuit is going to do. So this part, it doesn't get very complicated because N1 and N2, if they don't feed back into each other. In other words, we do not have a mini SR latch here, and as a result, the analysis is still just going forward. So in this case, D is a 0, and as long as D is a 0, N1 continues to be outputting 1, and that's what we'll say here. Okay, so we say N1.out remains as 1 because D is 0 and N1 is a NAND gate. The other one is a little bit trickier because En becomes 1. Let's see, I'm just looking at the text channel right now. Are the assumed changes from the original state or sequentially? It is sequentially. You can assume that it is sequential. In this particular circuit, it doesn't really matter that much because there's no mechanism feeding a later component back into an earlier component, so it doesn't matter whether it's sequential or not. But in the it's you can assume it is sequential, which means each state is following the one from before. But that's a good question. All right, but back in this case, En is changing from a 0 to a 1. So what's going to happen is now En is not going to determine the state or the output of N2, and only D is going to do it. But D is going through a NOT gate before getting into N2. So that means D, which is now 0, goes to the input of the NOT gate, and then the NOT gate is going to output a 1. So this time we do have 1 and 1 going into N2, and as a result, the output of N2 is going to be a 0. So that needs to be captured in writing. So we can say N2.out becomes 0 because one input has En, and En is a 1. That is given to us. The other input is the negated D. D is 0. So the negated D is 1. So that's sufficient as an explanation because we have a and N2 is a NAND gate. When both inputs are 1s, the output becomes 0. Okay, so that is a full explanation. Now, because N2.out is a 0, so our analysis cannot stop here. Because now when we look at the circuit, we can now see the R pin of the SR latch is also going to be a 0. So the behavior of an SR latch is when the R pin is a 0, it quote-unquote resets the state, which means Q becomes a 0 and then NQ becomes a 1, regardless of what they were from before this. All right, so that's exactly what I'll write in over here. So now we say, SR.Q becomes 0 and SR.NQ becomes 1 because SR.S is a 1 and SR.R is now a 0. And SR is a SR latch. Okay, there we go. All right. So I'm looking at the text channel. I thought there were a few people typing, and I don't see it. So that means those people either have not finished typing yet, or they decided not to type anything. Okay. So now we have the last state, which is both input pins are 1. So this is where it is sort of important to well, for this particular circuit, it doesn't matter, but for other circuits, it can be important because to rely on the previous state. So in this particular circuitry, I have to scroll back and back and forth quite a bit. Both inputs are ones. So what that's going to do is a few things, because D is going to be a 1, right? And then En is also going to be a 1, so N1.out is going to be a 0. So that is what we'll say first. Okay. Let me see if I can do this, because all this copying and pasting, excuse me, not copy and pasting, all this scrolling around is really kind of distracting. So I'm just going to paste the picture here, so this way I don't have to scroll back and forth. So now we say N1.out becomes 0 because D is 1 and En is 1 and N1 is a NAND gate. Alright, so that is a change from before. And let's look at N2. Okay, what about N2? N2.out. Is it maintained or is it changed? Now, because D is now a 1, the negated version of that is going to be a 0. So that alone is going to determine that N2 is going to output a 1. So we use the word becomes 1 because it was not, right? Because from the previous step, it was outputting a 0. Now it is outputting a 1 because En is a 1 and D negated D is, okay, D itself is now a 1, so not D is a 0, and N2 is a NAND gate. So with a NAND gate, anytime you have at least one of the inputs being a 0, the output is going to be a 1, and as a result, N2.out becomes a 1. So when you look at N1.out and N2.out, it is different from what it was before, and as a result, the SR latch is going to be affected as well. So now we have to say SR.Q becomes it becomes a 1. SR.NQ becomes, okay, I should be consistent here, becomes 0. Okay, because I use the word becomes because it is a change from before, because SR.S is a 0 and SR.R is a 1 and SR is a SR latch. There we go. So that pretty much finishes the question. This is a very simple form of propagation analysis. A more completed and more complicated one is the analysis of the edge-sensitive D flip-flop in the module that I have written. So I'm hoping most of you have at least read through that part and kind of went through the whole mental exercise of following the changes of the various components in that circuit. That is not necessarily a good idea, Alexander. Because some of the transitions can be so fast that you cannot see it. So it only happens, but it happens in an instant of time. So if you cannot see it, you may not be able to identify it, and that can, So the idea is you should be able to do this without Logisim, and you can use Logisim as a way to verify your understanding of how the circuitry works. Yeah, I mean, if you guys want to construct all of the circuitries, sure. I mean, before class, that's perfectly okay. But I'm not 100% sure that because Logisim doesn't explain, right? Because Logisim would just tell you, oh, okay, N1.out is now a 0, N2.out is now a 1. But it doesn't tell you why that is the case. And it is the explanation that is worth the points. Because I'm going to assume that people know how to recreate this circuit in Logisim. So if that is the case, then this part of the answer is worth almost nothing, because all that says is, yes, I know how to copy a circuitry into Logisim. I mean, that may be worth something in other classes taught by other professors, but in my classes, okay, I value reasoning. I don't value the skill of I can copy this circuitry into a tool, run that tool to find out, the output pin of a component is blah. That is worth almost nothing to me. All right. All right, so there are a few more text messages going. Yes, the truth table can be very handy. I think it is good in, okay, I hope it is good only in the sense of the feather that Dumbo holds. Okay, okay, yes, I'm referring to Disney movies, which I seldom do. Because I think at this point, most people should be familiar with the operation of the gates that we use the most, which are basically just AND or exclusive OR gates and stuff like that. But if you would feel more comfortable, you'll feel more confident because you have all the definitions, the truth table, handy, and you know where to find it. Do it, okay? By all means, do that if it can potentially help you. But I'm just saying that at this point, we probably should not be relying on a table to remind us the behavior of those gates. So that's all. Let's see. So there's a whole bunch more stuff going on. Okay, so there's a question of can I open example of exam? Not really sure what that means. Somebody posted a PDF of the same document already, so you can download that. Yeah, the gate truth tables, it's not so much memorized, it's just because you have used it so much that it is already in your head. It's just like, hexadecimal, to binary translation. I never really intended to memorize the table, but because I have used it, so much that I already have it memorized. And I do understand, terrible memory too, because mine is also kind of terrible. All right, happy thoughts and a sprinkle of pixie dust. Yes. The consumption of pixie dust during the exam is allowed. Let's see, it's good for verification. Yes. So have some tools to help you do the verification, but the tools that helps you with verification are not necessarily going to tell you the whys. Okay, but it's good to have those tools ready. All right. Well, in the actual exam, I'm doing it as if this is my exam. You just basically type your answer within the document. But you have to do it inside Google Doc, so don't try to download the document into a Word document, do it in Word, and then paste everything back into Google Doc, because you have to do all the editing in Google Doc. Okay, so don't do it offline and then copy it back. Yes, assembly coding is in the scope of exam 2, but without using subroutines. All right. The PDF is already made. Just go to the pinned messages. I think Omer, made a PDF document already. All right. So moving on. Question number 2. So there are still a few people typing, and I'm just gonna wait a little bit. There we go. Okay, so for Omar's question, subroutines are not in the scope of this exam, but coding without subroutine is in the scope. And the exam material does inclusively start from floating point representation, yes. And it end exclusively, with subroutine, which means subroutines are not a part of it. not so much the last lab, because the last lab, did some stack operation already. So stack operations are not a part of this exam, so it would be the one before that. So the absolute value thing is in scope, but the stack thing is out of scope. All right. So now we move on to one of my favorite questions, or favorite kind of question. Question number 2. So question number 2, you are given the pre-dissected microcode slice. So when you see the word slice in the context of microcode, all that means is just a location in the ROM of TTP. So it's already decoded, which means you don't have to figure out, oh, this is bit 22 and bit 23, and it goes into this tunnel, and so you don't have to decode the individual bits already. It is already decoded. All right, so there are still more things coming in from the text channel. We never looked at. Oh, sure we have. We have seen it all the time. Just not in a text file format. Okay, so let me explain what I mean by, yes, we have seen that many times. Oh, okay, that's my Windows virtual machine. Let me turn that off, because that is probably chewing up a lot of processing resources too. So let me shut that down. I was running a Windows virtual machine because somebody asked me something about how to use Vim or something like that in Windows. So I found out how to install that, and also how to get to Vim tutor and all kinds of stuff. How to get the content of Vim into the clipboard, that sort of stuff. So with that turned off, I can now go to my command line and start Logisim, because I want to show you guys what I mean by that. So history. Oh no, the previous command works. Alright, so here's Logisim, okay, and we'll just pick a particular instruction. Let me see, where's my cursor? There you go. Okay, so here's Logisim, and I'm just going to inject a certain location here because I don't feel like having to Control T through a bunch of times. So I'm just going to jump to location 400, which is I'm not sure whether you guys can remember this, but I have used this for long enough that 40 is JMPI. So this is the JMPI instruction. But the whole point is not even to explain the JMPI instruction now, but to look at, okay, what do you mean by the fully dissected, microcode slice? This is our microcode. So in order to figure out, what is in, let's say, ALUOP, there are a few ways to do it, okay? So what you can do is, you should know how to do this already. Just because I have not illustrated something doesn't mean that I do not assume you know how to do it, because you already know how a splitter works, right? You know what a ROM is. Well, that means you should be able to figure out how to figure out the value of this tunnel ALUOP from the hexadecimal digits of this location 400. Alright, so if anyone thinks that this is not a reasonable assumption, I'll just illustrate why I think it is a reasonable assumption using everything that you have already. Okay, let me rephrase it. Using everything that I have taught in this class. Just because I have taught it doesn't mean it is learned. So I make a distinction out of those two. But this is a good way to test, okay, whether you have learned the concepts or not. Alright, so the first thing we want to do, I'm just going to do this inside a notepad, just because it's easier for me to type here. So the first thing you do is you decode 1F80006 into, guess what? Ones and zeros, right? And someone is going to be smart and say, but Tech, you don't have to do this by hand, because you can just click on this thing here and it will give you all the zeros and ones. Yes, that's the other way to do it, okay? But just in case someone feels, okay, but I want to be able to do it by hand, and I really think that people should at least try to do it by hand once, just so that they learn the process of how to do this. Okay, so we have 1F0, 1F8, and then 0, 0, 0, 6. There we go. And each hexadecimal digit corresponds to 4 bits. I'm pretty sure I talked about this. And if you have the table, now we can just say, oh, 1 is 0, 0, 0, 1. F is 1, 1, 1, 1. 8 is 1, 0, 0, 0. 0 is 0, 0, 0, 0. And then 0 is 0, 0, 0, 0. 0 is 0, 0, 0, 0. And then 6 is 0, 1, 1, 0. Okay, now what do we do? Now we count, okay? So now what we do is we follow this output pin, and we know the destination. This is our destination, but it goes to microcode data, which is this thing here. So this, okay, let me just kind of magnify a little bit here. All right, so over here, because we know what a splitter does and how to read a splitter, so we know bit 3 to bit 23 are basically known collectively as microcode data, and then that in return splits into all of these things, and ALUOP is bit 13 and bit 15, but remember everything is offset by 3. So if you add 3 to 13, now we have 16, right? 16 to 18. Okay, so now we switch back to here, and now we just wanted to say, okay, what about bit 16 to bit 18? Where are those? This is the least significant bit. It is bit 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and here we have 16, 17, and 18. The 0, 0, 0. So now we go back to this circuit here, and then we ask, okay, now I have just confirmed that I know how to go from the content of the ROM of a ROM location and use all the tunnels, the splitters, and whatnot to find out, what a tunnel should end up with, as a value. All right, so now we go back to the yes. It's gnarly, and that's why it is already decoded so that you don't have to go through this trouble. But does that mean your question will not guarantee not to ask you to decode the splitter? No, I'm not making any guarantees, but I'm just telling you that in this specific case, everything is already decoded. So if everything is already decoded, what is the question? ROM 0 is just bit 0 of the output of ROM. So technically speaking, this is supposed to be ROM.D bracket 0, because ROM.D refers to port D of the ROM, and then the bracket 0 basically refers to just bit 0 of it, and then the same thing over here. So I'll be sure not to use the wrong notation here. There we go. All right, so now the question is, first, identify the components that are going to be updated. Okay, so the keyword here is these are the things that are going to be updated. This includes all the registers as well as RAM. So this is the big huge clue, right? What can update? Well, multiplexers don't update. I mean, they don't store anything, right? If they don't store anything, they cannot be updated. The ALU for the most part cannot be updated because it doesn't store anything. So only components that can store something can be updated, and there are only 2 types of components inside the processor that can store something. Those would be the registers and also RAM. All right, so now the question also says, for each identified component, explain why you think it is going to be updated. So tell me why from this list of thing here that you think it is going to be updated. Trace your reasoning to the bits from the data port of ROM. You may refer to these using the names in the pre-dissected microcode. Use the following area to answer this part of the question. Whew. So what do? Well, you just follow these things one by one. Okay, there's no real shortcut to do it, but it's not going to take that long. So now you first have to track down bit 0. Okay, and having logic sim or have a printout of the processor handy can be useful. Okay, so now we track this down, and we track down bit 0, which is this thing here, and then we say, is it controlling something to be updated? Okay, let's check out. It does. Okay, because it goes into the EN pin of the instruction register. But it is a, let me see whether it's a 0 or not in the case of the question. So in the question, I believe it is a 1. Okay, so since it is a 1, we know the instruction register is going to be updated. So we say since rom.d bracket 0 is a 1, the instruction register is going to be updated. Okay, that's 1. Let's see what else is going to be updated. RAM cell is a 1. Ooh, okay, so when RAM cell is a 1, we have to now check whether RAM is going to be updated or not. But the answer to that question is no. RAM is not going to be updated. It's not going to be updated because RAM load is a 1. So when RAM load is a 1, we are only reading from RAM, which means we are not updating RAM. So we do not put RAM on this list here. So moving on, RIMux is not going to tell us whether something is going to be updated. RIEN being a 0 means none of the registers inside the register bank is going to be updated. And if someone is asking in their mind, but why? Well, my answer is you kind of have to track it down, right? Yeah, so you have to go to the circuitry, locate RIEN as a tunnel, because I'm using exactly the same name as the tunnels in the question. So RIEN is this tunnel over here. So now you want to track down, what it is going to do. So when you track down RIEN, the only thing you can tell from the outside is it goes into the register bank. So now you have to track down what is inside the register bank, like here. And the EN is this particular pin. It itself does not automatically connect to one of the 4 registers, but it does enable the decoder, which then will send a 1 to one of its 4 outputs, so that one of the 4 registers would have the enable turned on. But that's only if this particular pin is a 1. Now, in the question, it is a 0, so that means none of the 4 registers, A, B, C, or D, is going to be updated. RI cell is just for selecting which register is going to be updated. Since none of them is going to be updated, this is irrelevant. RO, this is RO0EN, is register output 0 enable. That only determines whether register output 0 is going to be useful or not, so it's not going to control whether something is going to be updated or not. So it's not particularly helpful. Neither is this one, neither is this one, neither is this one, neither is this one, and ALUEN is a 0. When ALUEN is a 0, you know the flag register is not going to be updated. ALUOP is pointless when the ALU is not even enabled. And we go to ADDR mux. So that alone does not tell us what is enabled and what is going to be updated. So it's not really that useful. PC mux is 7. That alone does not tell us what is going to be updated. But the next one is important. Okay, the program counter enable is a 1. So that tells us that since PCEN is a 1, the program counter is going to be updated. There we go. Of course, you have to track down bit 24 and bit 25 too, but neither of those go to the enable of a register, so it doesn't really tell us what is going to be updated. So if I were to track down bit 24 and 25, when it's this one here, which goes into microcode pointer, It does update microcode pointer if it were a 1, but since it's a 0, it doesn't really do anything. And then the other one, which is bit 24, is only used to select how we're going to update the microcode pointer. But the microcode pointer is not going to be updated because it only updates on a falling edge. And the microcode pointer is one of the registers where we do not need to analyze because its operation is separated from the rest of the processor. All right, so getting back to the text channel. Is there a definition page for all of these tunnels? You're looking at it. What are you talking about? This is the definition. There's no more definitive definition than this. Yes, I copy that from Kung Fu Panda because in his dream he referred to himself as the legendary legend. Okay, there we go. Yes, I was just pulling your legs, Jonathan. Okay. So the key is to be familiar enough with this circuitry, okay, this diagram, so that you can relatively quickly locate where things are. Okay, and the key is really to locate where the register bank is, how it operates, because the name of the tunnel does reflect what it does. Alright, so we can skip the ones that don't do anything. Well, that depends on the question. I cannot just universally blanket and say, yes, you skip blah. Okay, but the question is specifically asking, identify the components that is going this okay, bad grammar here. Let me fix that. I cannot stand that. So identify the components that are going to be updated. Okay, so if something is not going to be updated, don't list it here. All right. Yes, David is asking a very good question. You can assume it is going to be a rising edge in this case, because the falling edge only affects the microcode pointer, which is the one thing that we do not put into this analysis. But in the exam, if you have a question like that, definitely direct message me to make sure that your assumption is correct. All right, very good. And then we have another question coming from Grant. Okay, so I'm going to wait a little bit. I just turned off my mic to drink some coffee. All right, there we go. So Grant is asking, so this question is having us first identify what the microcode is by the bit listed. So the bit listed is already kind of broken down for you. So all of these, the tunnels basically, and also some of the unnamed wires are already identified with the values already. So in this specific question, you do not need to like do what I did earlier in Notepad, to break everything down and count the bits and stuff like that. It's already broken down for you. And then go and check what is being updated. That is correct. So that's what step 1 is. All right. So the next question. I'm gonna wait for Grant to finish typing in the text channel. All right. Oh, okay. Sure. You're welcome. So the next part is to identify how these components are updated. For each component that is going to be updated, identify how it is going to be updated. Column C of the opcode table is a good example of what this part should look like. Okay, so you might want to go to the opcode table right now and look at column C and see what it looks like, and explain why you think this is how it is going to be updated. So hint, use multiplexers, demultiplexers, and possibly other components, and how other components are configured by the various bits. Alright, if you identify an issue where two components may specify different values on the same wire at the same time, also indicate that condition and explain why and how it can happen. Alright, so what we'll do now is to look at the two components that are going to be updated. One is the IR, the instruction register, and the other one is the program counter. Both of those are going to be updated. So let's find out, then what are we going to do now? Okay, so we look at the not this page over here. So now we look at the program counter, okay, because when we update the program counter, we have a starting point of tracking things down, right? So this is the program counter. When we update, we want to focus on this wire and go like, okay, what is going to be connected to this node? Unfortunately, it depends on this multiplexer. This multiplexer is selected by PCMux. PCMux is not a tunnel coming straight out of the ROM. Instead, it is coming out of this multiplexer here. I explained this part already, by the way, in one of the lectures. And this one is in return selected by PCMux. So we now need to know what is PCMux. So going back to the question, oops, not this one. So going back to the question, PCMux is 7. And then we go back to this diagram. PCMux being 7 means we are going to choose input 7 to connect to the output, which is PCMux. And phew, this is good because it's just a constant. It's a constant of 1. Okay. So now we go back and and explain a little bit in the question first, right? So go back to the question. Go back to the portion where we are at right now. So we now say PC dot D connects via a multiplexer, and the select of that mux is PCMux. PCMux equals 1 because PCMux is 7. So this is sufficient, okay, to explain, the first multiplexer. So now we look at the diagram and we say, okay, since PCMux is going to be 1, that means input 1 of this multiplexer is the one that we are choosing. Oh my! It's coming from another multiplexer, right? Okay, so now what do we do, right? So what we do is we look at PCMux and we look at RO0EN because that will determine the output state of this AND gate over here. I believe RO0EN is a 0, so we have a 0 coming in, but since this is negated before going to the AND gate, so we do end up with 1 and 1 being a 1 over here. So that means we are looking at this particular wire. So going back to the question, we say because PCMux is a 1 and RO0EN is a 0, the earlier mux or the preceding mux chooses input 1, which is connected to. Alright, so let's see where it's connected to. It is connected to the data port of RAM. Okay, so we can say RAM.D. There we go. Okay, so now we have just made a connection between the input to the program counter and the output of RAM, which makes sense because we know that we are reading RAM because RAM load is a 1 in this case. Okay, so now we can explain a little more. Okay, RAM cell is a 1 and RAM load is a 1. So we are reading the content of a RAM location to update the program counter. But we are not done yet, okay? Because which location are we reading? Okay, if you are reading a location in RAM or if you're writing to a location in RAM, you have to tell me what is telling you which location is being accessed. So that means we have to go back to the diagram. And this time we have to look at the A port, A for address. So we now look at the address and go like, okay, where is it connected to? Darn it, it connects to a multiplexer again. But this time the multiplexer is selected by ADDR-MUX. So we go back to the question again, and then we find out what ADDR-MUX is. And I have to look for it. Where is it? There we go. Okay, so ADDR-MUX is a 1. Okay, so if ADDR-MUX is a 1, it's selecting input 1, which connects to, guess what? The program counter itself. Okay. So now we go back here, and then we answer that part, and we say, because ADDR-MUX is a 1, PC.Q, which is the output of the program counter, connects to RAM.A, which is the address port of RAM. So that means, so PC determines which location of RAM we are reading. Okay, very good. Almost there, right? So now we have to, so this part, will give you PC equals to, star PC, using the notation of column C of the opcode table. But we are not done yet. We are not done yet, because from the earlier part of the question, we also know that the instruction register is going to be updated to, right? So now we say the instruction register is also updated by reading RAM, because it connects to the same node. Okay, when we go back to the circuit diagram and we look at the input to the instruction register, which is, nope, not this one, this one over here. That is the same thing that was used to update PC. It's the same node. So now we can say, oh, okay, the instruction register is going to be updated by the same thing. So that's why, we say instruction register is also whatever the program counter is pointing to. All right. And Chris is correct. This is not a real slice. Well, okay, it's not an actual slice of microcode in the ROM at this point. And I randomize a whole bunch of stuff, okay, so that things that really do not matter, I just go like, this can go anywhere. There's no particular reason why it cannot be this, right? Okay, so that answers this part of the question, and now we have the third part of the question. Does this microcode slice remind you of an existing instruction? Note that the dissected microcode slice of this question may change some additional registers, but as long as it does not interfere or prevent the processor from functioning, it is acceptable. So in this case, the instruction register getting updated is the side effect that did not need to happen, but it was specified. The dissected microcode slice of this question overlaps with the function of at least one existing instruction as described in the opcode table. Because when you look up the opcode table, you will find that JMPI has PC equals to star PC or asterisk PC. Find the instruction that overlaps the most with the given microcode slice of this question and determine the exact and specific mnemonic of this instruction. For example, CMPDA, use the following area to answer this part of the question. So the best we can do is to say, JMPI, and then we just say whatever, right? Because we don't know what to put here, because the microcode slice does not indicate the content of RAM. So we do not know what the immediate operand really is. All we can say is it's some kind of immediate operand, but we don't know what it is. It is not JMP, it is JMPI. If you look at the opcode table, you will see the difference between the two. Alright, last part. What is the hexadecimal opcode corresponding to this mnemonic? Use the following area to answer this part of the question. Okay, so looking up the opcode table, JMPI has an opcode of hexadecimal 40, or if you want to just copy the bit pattern, that's fine too, which is 0, 1. Oh, okay, I cannot use binary because the question specifically asks for hexadecimal. There we go. Alright, so are there any questions about number 2? It takes me a lot of time to explain, but if I don't need to talk at the same time and just kind of track down the wires, it wouldn't definitely be needing as much time. All right, so we got one question coming, and I'm going to scroll to question number 3. Yes, you could, but you have to be careful because you don't want to change the microcode of an existing real instruction. So you can just go ahead and find an empty spot and quote unquote implement your own instruction, and then you can use byte in a program to kind of inject that opcode into a real program, or just kind of overwrite the RAM content. Then you can run that cycle through and see what it does. We have 80 minutes for this exam, so it is not up until the lab, it's up until the lecture is over. There we go. You could do it that way, just change 3FD, but 3FD cannot be executed using the normal fetch cycle. If you want to be able to use the normal fetch cycle, it has to end with a 0. So you have to find a location in ROM where the least significant hexadecimal digit is a 0, and the content is all 0 except for 010, which is the halt instruction. Then you can go ahead and basically hijack that location to implement your own opcode. How fun is it, right? I mean, you can implement your own opcode by specifying the microcode of what you want to do. All right. So what Tom is mentioning, will there be practice we can do over the break, or an assignment like Canvas, to tell us whether we are right or not? Okay, so what you can do is to at least understand all of the opcodes that we have used to date, and understand how they operate. Not really just looking at column C of the opcode table, but also looking at how the processor, how inside the processor, the multiplexers and demultiplexers are configured to get something to do something. And I would think the conditional branch instructions are a little bit trickier than others. Increment and decrement are also kind of tricky, even though they seem simple. They're actually a little bit tricky as well. Let's see, what else would be tricky? If you want to try something that is not tricky, copy register, CPR, is actually really simple. I mean, that's a good way to start kind of looking into those things. All right, so now we move on to question number 3. So question number 3 says, let's start with the value in base 10, which is 9.875. In the conversion of this value to a double precision floating point number bit pattern, a mistake was made, and the implicit 1 point part of the mantissa was actually included in what would have been just the fractional part of the mantissa in a double bit pattern. When I use this double here, it really is the short form of double precision floating point number. Okay, the rest of the conversion was correct. Due to this mistake, what is the actual value represented by the erroneous double bit pattern? Using the following area to answer this question. Use the following area to answer this question. Your answer should demonstrate your understanding, knowledge, and problem-solving skills of double precision floating point numbers. As such, correct final answers without proper intermediate steps do not get any points. Alright, so the first thing is to understand what the question is asking. right? So the question is basically saying, okay, this is the value that we want to convert into a double. But in the process of converting into a double, there's one part of a double where we're supposed to store only the fractional part of the mantissa, but the mistake was made, and instead the entire mantissa was stored, including the one from the 1 point is also stored at the portion where only the fractional part was supposed to be stored. So the question is really asking, because of this mistake, what value was actually represented by the double instead of what it should be, which is 9.875. That is what the question is asking. So do we have any questions about the question itself? What the question itself is asking? Okay, I'm not seeing any. Okay, there we go. We got some traffic coming in. Oh, we got a whole bunch. Cool. Okay. We're trying to figure out how wrong the answer is. How wrong is the erroneous conversion? So instead of representing the value of 9.875, instead, what was actually represented? That's what the question is asking. And then Mohammed said, so we have to find out what was the answer because of this error. No, we want to find out what value is represented instead of 9.875. And then Chris is, well, I haven't really done it yet. He's probably correct. Okay, Chris is probably correct, but I haven't done it yet. So let's go ahead and do this. Okay, so we'll go ahead and figure out. Okay, so to figure out what bit pattern is actually stored. Okay, so now we have to look at 9.875, and we want to convert it into a base 2 representation. So there are many different ways to do this. Okay, there are multiple ways to do this. Googling is not one of them. Because if you try to look up, what is the double representation of, some particular value, I'm pretty sure there's a website that has a calculator to do it. But the calculator is not gonna say, well, but if you made a mistake like this, then you will be representing that value instead. That does not, I have not found a tool that can do that, and and I mean, kind of, the way I designed the question is to kind of make sure that the answer cannot be easily Googled using an automated tool, because I want to see whether you can do the job, not whether you can find a tool to do the job. So that's kind of how it goes, right? All right, so we want to convert this into base 2, and this is 1001 point. Let's see, we got 1/2, we got 1/4, and then we got 1/8. Okay, so that is the conversion. And the conversion process itself, you can explain it. Okay, so we can explain this, right? We can just explain it. I mean, the more explanation you do, the less likely I will take points away, because you did not demonstrate the steps. So we'll say it's 8.8 plus 1 plus 0.5 plus 0.25 plus 0.125, which is 1000 in base 2 plus 1 in base 2 plus 0.1 in base 2 plus 0.01 in base 2 plus 0.001 in base 2, which is then 1001.111 in base 2. Okay, so there we go. We have one line to explain how to convert from 9.875 as a base 10 number to 1001.111 in base 2. So now from here, where do we go, right? Okay, so now we want to normalize the mantissa. So now we say 1001.111 in base 2 is, if you don't want to do this step by step, that's fine. You just say 1.00 1, 1, 1, 1 in base 2. But then you have to say times 2 to the power of, let's see, how many times did we move the binary point to the left? 3 times. So we have to specify that. So now we know 3 is our exponent in base 2. Alright, so let's see. I have to read the question again and find out exactly what I need to provide as the answer. Your answer should demonstrate. Okay, so whether you know that you have to use the biased notation for the exponent is not super duper important, but I'm going to do it the right way. I'm going to do the entire conversion, right? Okay, so I'm going to say because of the mentioned mistake, the value is represented as follows. Okay. Oops. There we go. The sign is 0. The exponent, the biased exponent is 3 plus, the 3 is coming from this 3 here, plus the bias amount, which is 1023, which is 1026, which is 1 followed by 10 zeros, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, except we have a 2 down here, so it's going to be this particular format. And then the erroneous mantissa part is, now this part is incorrect because of the mentioned error. So instead of only using the fractional part of the mantissa, which is only supposed to be this part here, whoever did the conversion also included the 1 in as a part of that part. So the erroneous mantissa part is now 1, 0, 0, 1, 1, 1, 1, and then the rest are all zeros. Okay, in base 2. So now the actual representation is going to be 0, followed by the 11 bits for the biased mantissa, like so, and then followed by the erroneous fractional part of the mantissa. Okay. But so now I'm going to say, but the actual value represented by this double is 1.1001111 in base 2 times 2 to the power of 3, which is 1 plus 1/2, and then we have, let's see, 1/4, 1/8, and then 1/16, 1/30th, 1/32nd, 1/64th, and finally 1/28th times 8, right? Because 2 to the power of 3 is just 8. So now we just do the calculation. So that becomes 8 plus 4 plus 0.5 plus 1/4, right? And then we have an 1/8, 125, and then we also have a 16th. I'm just doing the mental math, because I'm just saying, okay, what is I'm just multiplying each one of these by 8, because, okay, yes, it's my bad. I should have used parentheses here. So I'm just distributing and doing the mental math at the same time. So now this one is 0.625, I think. So now if you add up these numbers, you get the answer. If you get to this point, I'm not going to be picky and go like, but I want a single number as the answer. No. If you get to this point, I will count it as the correct answer. Okay, so questions? That is not a question. That is correct. So Chris is correct because the problem is with the mantissa part and not with the exponent part. So we know that we are still preserving the exponent of 2 being 3. So whether that really gets converted, based on the biased amount or not is not important. And the question itself did not ask about the bit pattern of the erroneous representation. Now, if the question had asked about the erroneous representation, then you will have to go through this process. It would not have been optional if I did ask for the erroneous double representation. Yep. So the middle part can be skipped. That is correct. Because the key really is the original mantissa was this. But the actual mantissa based on the erroneous representation is going to be this. And that's why that's why the value is wrong. It's off by a little bit. Okay. Okay. I'm still in the process of doing it. I'm sequentially going through the submissions, and I'm going through every single one question, and reading everything so that I read the reasoning of why someone think those bits should be a 1 or 0 and so on. So it does take a long time. And I do apologize that it's taking this long to do it. I underestimated how much time it will take to grade it. I think I can give you guys your own exam. For exam 1, I can make you a viewer of your own exam, and I can have the automatically generated key as well. So that way you can at least tell whether you got the right answer or not. So I think that should help. That should help with people who are anxious because they don't know whether they got the answers right or not. So I can do that. That part is kind of mechanical. Assigning points is not mechanical because I have to actually read the reasoning of how people reason things out. We got a few more people typing. I'm gonna wait. Let me see. Let me take a quick look here. So I got a few graded. Because I can tell how long it takes to grade 1, and then I can guesstimate how much time it will take to grade the rest. And this is also a big class too. That part doesn't help. Alright, so there's one more. Okay, Zoe is asking to go over the circuit in Logisim right before the exam. Okay. You have to turn it in Google Doc. I'll put it this way. I will only grade the answers as submitted by Google Doc. And Andre did the actual calculation. Okay, so very good. That doesn't look right to me. 9375. That. Oh, okay, maybe it's right. Or did I make a mistake? No, I didn't make a mistake. Okay, so that's probably right. Okay, never mind, my mistake. There we go. Let me show you guys something that I learned, as I was grading the exam. I found this really kind of cool tool. So there are a few things I want to show you. The first one is the history of editing. So I can actually go back in time and find out all the editing that I have done. So this is kind of interesting, because I can click on any one of these and it would highlight the change that I made at that point in time. So I find this kind of interesting. And then the other thing I want to show you is even more interesting. So let me go to Google Chrome. This one only works in Google Chrome because you have to install an extension first into Google Chrome in order for this part to work. So let me copy and paste the URL. So copy and paste. There we go. Alright, so here's Google Chrome, and I have installed two plugins. One is called DraftBack, and the other one is called DocuViz. Okay, and they do about the same thing. They're visualization tools to track the changes of a document. So this part is useless because it doesn't include what is already in the document. But this one also gives me a graph. So this is the x-axis is time, and then the y-axis, interestingly, refers to the position in the file. So if someone is to kind of go forward and then backward and forward and backward, I would be able to see that. And if somebody pastes in a whole bunch of content, I'll see a big chunk of block, like vertically, within a very short amount of time. So that is kind of cool. And then the other tool is DocuViz. So this one gives me a slightly different view of the document, what the original is and where I insert my the new content, or where I made all the editing. So this gives me kind of a view of how things got changed over time as well. It's just a different way of presenting kind of the same information, but in a slightly different way. There we go. These are really useful because if you have to co-author a document with a whole bunch of people, and there's a slacker within the group, you can use color coding in that case to see who contributed how much, at least in terms of volume in a document. And if you see somebody has a color that is completely missing, then somebody has not done a single thing. Paste one line at a time. Yes. Let's see. Okay, so Anne-Marie got the same answer. I'm just going all the way back, and that is the correct answer. So Andre got the right answer. All right. Well, in Discord, you can say mean things about me and then delete those. You do have permission to delete your own text in Discord, but not in the exam. Write a bot to Google the answers. I mean, you guys can use Google. I mean, you can legitimately use Google in my exams because, I think, if you can just Google something and you find it on the internet, hey, that's fine. But that's also, kind of the way it's the assumption that I make, when I design my tests is, well, I need to make sure that people cannot just Google the answer. Yeah, I mean that's perfectly okay. I mean, if you want to look up, two's complement using Google just to find out, just to remember, what it is and how it's done, that's perfectly okay. Not a problem. Yes, I did say, yeah, I'm gonna post. I can show you what it looks like. Okay, the key of exam one. Give me a second here so I can find it. Because when I generated the questions, the same script would actually generate the key as well. So let me. Oh, it's not in HTML. It's in Markdown. Well, that's okay. We can do Markdown. So let me. Okay, I can do this. There we go. So this is what the key looks like. It is mechanically generated. It doesn't explain, how the bits are, become the way they are. And that part I kind of have to manually evaluate anyway. So it does give you all the answers, to the fill in the bits part. The other two parts I can eyeball pretty quickly, like, what is the signed versus the unsigned representation of a bit pattern. That part I can eyeball, that's really quick and easy. And then the last part is also pretty easy because if I know x and y are both 101, well, I mean, this is the easy one. Let's pick this one here. If I know x is 111 and y is 100, because we're dealing with addition, so p is the or between the two, so p in this case would also be 111. But because g is the and between the two, so the g is going to be 100 in this case. So those are the easy parts where I can just eyeball. I don't really need the key to tell me what the answer is supposed to be. But this part, I can then, kind of cross-check, the answers submitted and see whether the bits are worked out, the way they're supposed to. So I can post this. Yeah, I can, and that's what I said too. Is I would also share, with view-only permission of your own exam one. So everybody would get exam one back, view only or comment only, because then you can add comments, and that's how I would grade it too. Is I'm gonna comment on those submissions because I need to jot down notes of okay, I can see this part is correct, this part is correct, this part is not correct because of blah blah blah, and I do that with every single question of every single test. So it takes a while. So that way you can, um, yeah, exactly. It's not exactly view only, it is comment only, which means you cannot change the content, but you can add comments to it. So you have comment only access to your own answer plus the key. And I think I can make the key a little bit more elaborate. Basically it would also do the explanation of how to find the bits in what order. I think I can do that part because I think the logic is still in the program. I just did not capture that part of the output. So that way, you would have your own answer and also the key, which not only contains the final answer but also the reasoning. But it's kind of mechanical, but nonetheless, the reasoning of how to figure out the bits. All right, and that part I can do, pretty quickly because it's all kind of mechanical. Yeah, sure, absolutely. All right, I'm just looking at the time. It is close to 7 o'clock. All right, so there's no lab today. And, so technically speaking, if you need to sign off or want to sign off, go ahead. But what I would do right now is to kind of illustrate um, to people how I would study for this test if I were my own student, which is really hard because I kind of have to have induced amnesia first, because then otherwise I have all the knowledge that I need already. But if I were to study for this exam or for any exam, so it's a kind of more general approach, is this. Okay, this is really the key to kind of prepare for the test. So what I would do is I would go to the opcode table and pick one of these instructions and go like, okay, I want to know exactly how it gets something done. So I'm going to pick an awkward one. Okay, I'm going to pick JC, which is not junior college. Okay, jump if carry. Okay, this is jump if and only if carry is a 1. So I would look at this instruction and go like, that's a really kind of odd looking instruction. It does use a register because X and Y are placeholders for registers, and we can see XX in the bit pattern here, basically saying, hey, XX, those 2 bits will specify which register is being specified. But why do we need a register in a JC instruction? So when you look at the notation in C, which is also coincidentally in column C, it says we would update the program counter. How do we update the program counter? We'll update the program counter based on C as a condition. C as the carry flag is a condition. If the carry flag is a 1, which means it is true, then we will use the register to update the program counter. If not, the program counter will get itself. Basically, this is just saying, no update to the program counter. Okay. So I'm just going to say, okay, let's check out this instruction here and find out what happens when I want to use, say, register B to update the program counter, but only if and only if the carry flag is a 1. So the first thing I need to do is to do a hand assembly of the instruction, or if you want to use the assembler, that's fine too. So that would be, let's see, we have a B as the most significant hexadecimal digit, and then a 0110, which is a 6, as the lower hexadecimal digit. So we have a B6. There we go. And then we go to the processor and just basically plant that instruction here. Okay, so we just plant the instruction into the microcode pointer. The alternative, okay, you can also use an alternative. Let me reset the entire simulation first. Reset. So the alternative is really just to punch in the opcode in RAM and just let it run. I mean, that's fine too. But you don't want to just let it run. You want to single clock until you get to that location. So I'm going to punch in the code here, which is B6. And then we single clock, use Control T. So make sure that you can explain to yourself what is happening for each transition. So Control T, this is the fetch, which basically you can see how B6 is put into instruction register. Then we increment the program counter. Okay, so let me check the program counter. Program counter is now updated to 0, 1. And then we decode. And after we decode, this is the key. Okay, this is going to specify the actual bit pattern so that we configure all the multiplexers and demultiplexers and registers and RAM, so that we get the job done. So now we go through the analysis, right? So we go through the analysis. I'm not gonna ask you guys to manually decode what goes into RMux, what goes into REN and whatnot. That is way too mechanical, and I don't think it's a good use of your brain juice. So instead, you should focus on what is happening here. So we can see RAM is not selected, so RAM is not being used. So now, how are we going to update the program counter? So the first thing is to make sure that we are indeed updating the program counter. We can see PCEN is a light green, so that means the program counter is going to be updated. So now we follow the same track of reasoning, which is to look into the input to the program counter. It is not selected, so or more importantly, it is determined by PCMux. So now we look at PCMux, right? So PCMux is up there, and now I understand why Aaron says, well, how come, Logisim doesn't use the scroll bar? I mean the scroll wheel on the mouse. Yep, that's kind of annoying. So anyway, so now we want to look at PCMux. Yeah, vertical scroll, and horizontal scroll is kind of useful too, and it doesn't work either. Okay, so PCMux is 0, 0, 0, which means we're connecting input 0 of this multiplexer to PCMux, which in return is the select of the multiplexer going into the D port of PC. So this is really important because what is input 0 of this multiplexer? It comes from bit 0 of the flags register. So when you look at the flags register, then you go like, but how do we update the flags register? So this part, you can just have a table, to kind of remind you, what is bit 0 of the flags register. If not, okay, you can still use the time in the exam to go into the ALU, go all the way down to, this portion here where all the bits, merge into the output pin. So now you can see, bit 0 is corresponding to the carry. So the carry bit, is bit 0. All right. So eventually, basically what this means, okay, is the carry bit is being used as PCMux. Okay, in other words, PCMux here, this really is the carry bit. So if the carry bit is a 0, then we select input 0, and that is coming from, guess what? The adder. Then you go like, oh no, we are going to skip a location then. Well, we are not going to skip a location because the carry in is a 0. Okay, most of the time it is a 1, but this time it is a 0. So we can see PC Inc is a dark green, and then address mux is also a dark green. So address mux is coming straight from the ROM, so we don't have to explain that one because it comes from the ROM. But PC Inc does not come from the ROM directly. PC Inc is a tunnel that is based on some kind of calculation. And I cannot remember where I stashed it. Alright, so this is why Logisim is kind of cool because it highlights the whole tunnel. And alright, so let me zoom out to find the PC Inc tunnel. To the very right. There we go. PC Inc is right here. Alright, so PC Inc is right here, and so PC Inc determines whether to increment the program counter or not. And you can see how the output PCMux is fed into the first 5 bits. In other words, PC Inc is also really just the carry bit itself. So since PC Inc is really just the carry bit, which is 0 in this case, so that's why we have 0. Okay, getting back to here, that's why we have a 0 as PC Inc, because that really is just the bit that we are interested in. And then ADDR mux is coming from the ROM, and that is how the ROM specifies, which is a 0. So 0 or 0 is a 0, and that's why the incrementer, even though it is active, it is not doing a single thing, because whatever the program counter is going in is whatever the program is the same value coming out, and as a result the program counter is not changed. That's how we do it. Yeah, that's how we can say the program counter gets itself back, which is not changed. Now, how do you make sure that when the carry is a 1, then it would actually do something differently? So the way you do this is to go to the flags register, and instead of having 0, 0, now it has 0, 1. This one, which is the least significant hexadecimal digit, is specifying that the carry bit is a 1. So we can already see how bit 0, is now a 1, and we can also see how quote unquote a copy of that is also going to be a 1, and that becomes PC Inc. But PC Inc is irrelevant in this case because PC Mux is already a 1. When PC Mux is a 1, we are using input 1 of this multiplexer to connect to the output. So now we have to track down this wire. This wire goes into another multiplexer, and this multiplexer is specified by PC Mux and RO0EN. RO0EN in this case is enabled. So now we have a 1 which is negated into a 0 going into an AND gate, and that's why the output of the AND gate is guaranteed to be a 0. So that means we have to track down this wire instead of the other one. And it comes out of a demultiplexer here. This demultiplexer, this is the output of the demultiplexer, this is the input of the demultiplexer. So just because it is coming out of output 0 of the register bank doesn't mean it really is connected. So now we have to make sure this demultiplexer is indeed active, and RI register output 0EN, RO0EN is a 1, so that means the demultiplexer is actually active. And then when we click on this select wire, it is selecting 0, 0, which means input is connected to output 0. So now we know that the output 0 of the register bank is connected to the program counter. But how do we know which register of the register bank is driving or specifying output 0? So now we go into the register bank, and we can see how register output 0 select is a 0, 1. So this is the same wire. This is the wire that would select which input of this multiplexer connects to the output. So since it is specifying a 0, 1, so we track down this wire, which is coming from register B. So this is how we can establish the entire path that the output of register B in the register bank is connected to the program counter, which is about to be updated. And that is why in the opcode table, where is it? Oh, right here. That's why it is using, that's how we specify which register to use to update the program counter, but if and only if the carry flag is a 1 in this case. Yes, it is still being recorded. I have not stopped the streaming yet. Yep, we are still on. Alright, so, and Nathan asked what is RO0? Is register output 0 of the register bank. So the register bank is kind of its own kind of interesting thing because it's basically a switch. It's an array, so to speak. It's an array of registers. There are 4 registers in the bank, and we can select any one of the 4 as output 0 and select one of the 4 as output 1 simultaneously. Not all operations would require both or one of the outputs. Some operations does not need the register bank at all. Okay, so for those operations, none of the registers, it doesn't matter because it's not connected to anything useful. But in this case, it is only using one register, and that usually comes from register output 0. So that explains what is RO0, register output 0. All right. So this is what I would recommend you guys to do, is to pick, let's say, another instruction, right? And just kind of figure out what it does and how it gets it done. Okay, so the important part is not so much what it does, which is documented by column C, or just column D is the kind of the explanation, not explanation, but description of what it does. But what you want to do is to go into the processor and do what I just did to kind of locate how something is done. it is a tedious process. Yes, I understand this part is kind of tedious, but at the same time, if you choose different types of instructions, it would also tell you how those instructions are implemented using the microcode, using the content in ROM. And I think that's going to be a useful process because by doing this, you would know where the tunnels are. Because even I could not remember where PC Ink is because I don't use it very often. So by doing this, a few times, I think you will start to develop a mental map of where the components are in this diagram. Now, obviously, highlighting, using post-its, and using your own way of annotating, this circuitry is going to be helpful as well. Okay, so I'm reading the text from the text channel. Did I see more floating point conversion related material referenced earlier? So there's only one question in the test in the exam that we looked at today on double, and I think that's going to be the case in your exam as well. It's only having one question on double. Alright, so we got some more questions coming. Two more. Alright, so Victor beat the other two. To answer Victor's question, I kind of, I'm not a very good planner. Okay, when I do something, I just kind of jump in and do it, which is not really a very good example for you guys. But that's kind of what I did with the processor. Was I kind of have an idea of how to get certain things done, so I would do it up to a certain point, and then I would get stuck, doing the next thing. Then I would kind of work on it a little bit, and sometimes I need to kind of rip the whole thing apart because I forgot to do something. So that's kind of the process of how I came up with the design. The microcode, interestingly, the ROM component was narrower. Okay, so I didn't use as many bits per location, and I had to change the structure of the ROM because, oh darn it, I need one more bit to do this, so I need to make it longer, and then I have to redo all the tunnels and redo the splitters and all kinds of stuff like that. So it went through a few iterations like that to get to the current point. All right. I thought you responded to this with more practice questions. Oh, I don't remember. Okay, so if you want a practice question, you can go ahead and pick a value to convert. So I'm just I'm thinking about how you can come up with a reasonable value to convert, because certain values are they don't seem to be difficult, but when you try to work on it, you go like, oh, this is really hard. Something like 0.3 in base 10 is really hard to do, to convert into double, because it's kind of like 1 divided by 3 or 10 divided by 3 in base 10. It just generates a recurring pattern, except this time the recurring pattern is in binary. So what you want to do, it would be a mixed fraction that has a fraction side where the denominator is a power of 2. Okay, so that's the best way I can describe it. So something along the line of like 7 and 13 divided by 64, something like that. Okay, so use that as a test value and try to convert it into a double. Okay, so in the lecture where I talked about the double representation, I kind of showed a trick that you can do in GDB so that you can double check to make sure that the binary bit pattern does represent the value that you intend to represent. So you can use that to verify your understanding of the conversion process. Okay, so this is the base 10 value. If I want to convert that base 10 value into a double, I went through this process, but did I get the right bit pattern? You can double check and make sure that you got the right bit pattern. So the idea is, you have to kind of learn how to do it by hand. And once you do it by hand and know how to do it, it's not really that difficult. It's not that much of a chore. As opposed to people who just want to Google it. All right, next one is from Jonathan. What is the estimated weight of each question? So they are supposed to have equal weights. The previous exam is a little different because all the questions are of the same type. They just have a different level of difficulty. So they're basically all testing for the same kind of knowledge and the same kind of problem solving skills. Just with varying degrees of difficulty. But for this test, the questions are not the same. So as a result, I cannot just go like, okay, I can see, you understand how to do this, and you cannot answer those other questions because you just ran out of time. So in this one, because they're all asking for different things, they're testing different kinds of knowledge, so I cannot use the same approach as the first test where, I can look at one completed answer and go like, yeah, this is evidence that this person knows how to do this. Yep, 80 minutes. The lecture portion of the class. Well, interestingly, during the exam, you can also watch the recorded YouTube. Not recommended. Just because you can do it, you're allowed to do it, doesn't mean it's a good idea. Unless you have a bookmark of all the important stuff. So you can jump right to the point where, this is the crucial part where Tech explains something. Okay, what is the bias of the exponent? Then it might be helpful. But, it's probably not a good idea to go through, like 20 minutes of lecture just to find something. All right, next question. If there are no further questions, I'm going to stop the live stream, but as long as we still have some questions and people want it to be answered, I can stay on here. I guess wing it is one way to put it. Okay, so there are two ways. There are two kinds of ways of preparing for a test. I'm going to use Legos as an example. So one way to prepare for a test is basically the professor saying, I'm going to have you guys to make, I don't know, a race car out of Lego pieces. Remember all those race cars that we have already made before the exam, with all the labs and all the exercises? So we're going to do another race car with some minor, really, really minor modifications and changes. So that's probably, the kind of the usual way for professors to make the test is, they're basically just testing whether people can replicate the same process, the same steps with minor variations. But the way I do my test, the way I write my test is to say, okay, see in class, I showed you guys how to hook up, block A to block B and C. And then I show you how to hook up block B to block D and F. And then I show you how to hook up these blocks. So I show you all the small pieces of the how blocks can link to each other. And then I also show you a structure where we have multiple pieces and they're linked or they're constructed in a certain way. But in the test, it's going to be something else that I want you to make out of the same kind of pieces that we have talked about in class. But the way you hook up things would not be exactly identical to something that we have seen already. So I'm basically testing, one, do you know what piece can hook up to what other pieces? Okay, that's the most basic part. But the most important part is, this is the finished product. Do you know how to use the pieces that we have already talked about and your understanding of how these pieces can hook up to each other so that the you hook up all of these pieces to make the finished product. So that is the kind of question that I would ask. I wouldn't say it is winging it. I would say it is a dynamic application of what you have learned in class in the form of problem solving. I mean, some of you can still say, yeah, that's just a fancy way of saying winging it. Alright, so I want to see if there are any more questions. Looks like we are good for now. Oh, time is one coming. I can still answer questions on the text channel. The question is, do I still need to stay on YouTube? Because right now it's I'm not doing anything with the screen. Yes, I will be available during the break. But the response time, is well, according to the syllabus, the turnaround time, during a break or over the weekend is 48 hours. It typically would not take that long, but it's I'll get to it when I get to it. All right, you're welcome. And let's see. Nope, I did not say I would have exam 1 graded tonight. Well, not today. Alrighty. Okay. So looks like we don't have any further questions that require live streaming, so I'm going to